Hello, I'm Brian Young. And today we're doing Module 26207, Cable Tray. Let's get started. 26207, Cable Tray. Successful completion of this module prepares you to do the following: identify cable tray components, explain how to select cable tray fittings, identify cable tray support components. Cable trays are commonly used to support cable systems in industrial applications. This module covers various types of cable tray and their support systems. It also explains how to determine the structural load applied to a cable tray system and calculate the allowable fill for NEC requirements. 1.0.0 Cable tray components. Explain how to select the cable tray fittings, identify cable tray support components. NEC Article 100 defines a cable tray system as a unit or assembly of units and fittings that form a structural system used to securely fasten and support cables and raceways. Cable tray is not a raceway. Cable tray is a support system. So cable tray itself can be installed in hazardous environments. It depends on the type of cabling or conduit system you put in the cable tray that determines the if it's hermetically sealed, if it's intrinsically safe, what have you. If you're using tray cable or if you're using armored cable, it has to be acceptable for the location, for the class and division of the hazardous area. NEC Article 392 covers cable tray installations along with a type of conductors to be used in various systems. Whenever a question arises concerning cable tray installations, this is the NEC article to consult. Then I have a highlight cable tray, NEC Article 392. Cable trays are common means of supporting cable systems in industrial applications. The trays themselves are made up into a system of assembled, interconnected sections and associated fittings, all of which are made of metal or non-combustible material. The finished system forms into a continuous rigid assembly for supporting and carrying single conductor, multi-conductor, or other electrical cables and raceways from their origin to their point of termination, frequently over considerable distances. Here's a highlight. It says non-metallic trays are also available. They're ideally suited for use in corrosive areas and in areas requiring voltage isolation. Here's another highlight. This says cable tray is available in various forms, including ladder tray, trough, basket tray, and center rail cable tray. All can be supported from the side except for center rail, which must be supported from the center rail. Center rail tray is also referred to as monorail tray. There are some places that won't let you use it. They don't allow center rail tray. This is a trough. From what I've seen on the job, trough is usually smaller, 4 to 6 inches, and it's to branch off of a cable tray system to bring one branch circuit or one motor feed, one feeder to a certain area. You'd use the trough. This is basket tray. It's lighter weight. It can't carry as much weight, but it's easier to install. It's usually used on low voltage, maybe communication cables, things like that. This is your single rail, the center rail or monorail tray. Like I say, a lot of places don't allow it because when you suspend it from the center rail, if you load one side with more cables than the other, it has a tendency, there you go, it'll tilt one way or the other. And if it tilts too far, some of the cables might fall out, or it may hinder the ability of the system supporting the tray. So, like I say, some places don't allow it. This lightweight, flexible, non-metallic cable management system is used to route wiring to large motors and similar loads in a manufacturing facility. So, this is also sectional and it can move. So if the thing that it's attached to is going to trolley, if it's going to move along, this will allow that movement to happen. It'll double back on itself like a bicycle chain. So it allows for that movement and still keeps the cable safe. Ladder tray consists of two parallel channels connected by rungs, similar to appearance to a ladder. Ladder tray offers a good air circulation around the cables and helps dissipate heat. The rungs are convenient for tying down conductors and will not collect water from rain, roof leaks, or condensation. So here's a highlight that says trough tray consists of two parallel side rails with a corrugated, ventilated, or solid bottom. Various tray types and fittings are shown in figure 5. So here's a good map. You should go over this. You should especially look at each thing. You can have solid bottom trays. If you put a solid cover on a solid bottom tray for more than 2 feet, you have to derate the ampacity of the conductors in that tray because it's not allowing for dissipation of heat as well as the corrugated or the rung cable tray or the ventilated trough. So you have to take that into consideration. If you go through an area with a hazardous atmosphere, you may have to run a solid bottom tray with a solid cover to add to the safety of the system. But there again, you have to reduce the ampacity. Here's a barrier. It will separate low voltage and high voltage cables from each other. This is a horizontal cross. Here's a horizontal T. They have horizontal 90s or what they call elbows. Here's an outside L. There are also inside Ls. I don't see a good example of an inside L here. If we were traveling along and we needed to turn up, we'd use an inside L. And the rungs would be on the outside of that radius or the 90-degree bend. This is an inside L. I'm sorry, this is an outside L where the rungs are on the inside of the radius. So you can take cables on the outside of it. Again, they have inside Ls and outside Ls. They have flat Ls. Here's an offset. Here's what they call a horizontal Y. It's not necessarily a T. It's when you're going in the same direction, but you want to split off. You can put this Y on there. They have reducers. They have cover clamps. So all of these. Here's a vertical T where the conductors on this side would cascade down, and the ones on this side you'd have to feed them through because they'd end up on the outside of these corrugated or rungs. Cable trays generally manufactured in 12 feet and 24 feet lengths. That's a highlight. Most of the companies I've ever worked for buy them in 12-foot lengths. Common metric dimensions for cable tray are 3 and 6 meter. Common widths are 6 inch to 36 inch and depths of up to 6 inches. Cable tray fittings have horizontal and vertical T's, Y's, horizontal and vertical bends, horizontal cross, reducer, barrier strip, cover, splice plate, box connector. We've kind of looked at all of those on that last page. The area of a cable tray cross section that is usable for cables is determined by multiplying the width by the depth as shown in figure 6. The overall dimensions of the cable tray, however, are larger because the side flanges and seams. Therefore, the dimensions including the usable area vary according to the tray type. Cables rest on the bottom of the tray and are held within the tray area by 2 longitudinal side rails. These are the side rails. So you can see here they're saying that this flange means that the cable tray itself is wider than the usable space. Channels used to carry one or more cables from the main tray system to the vicinity of the cable termination. Conduit is then used to finish the run from the channel to the actual termination. Unless it's a motor and you have flexibility, then the very final feed has to be flexible metal conduit or the cable itself going to the motor. If you're in an industrial establishment where only qualified personnel will be servicing this motor, then you can run just the cable itself. You don't have to have it inside of the flexible raceway. And this is dropping out. So you can either use channel to drop out, or you can just come on the side, let the channel drop down, and then you come into it. Cable entry and exit. Cables are placed in trays either by being pulled along the length of the tray or by being laid in over the side. Figure 9a shows a conveyor sheave being used to guide the cables around a turn, while Figure 9b shows the cable tray roller clamped to the side of the tray. So here are cable sheaths used for pulling. It keeps it from rubbing on the inside edge of the cable tray itself. And here's a roller guide. So here's a highlight. It says, for example, adding dropout between the rungs, or, and this is the highlight, dropping the cable from the end of the tray without using a dropout plate may be prohibited by job specifications. You need a dropout plate. The dropout plate makes a nice radius. A metal plate used at the end of the cable tray section to provide an acceptable cable bend radius as the cable drops out. You can use that dropout. You can use a dropout plate inside the tray. So here's a dropout plate holding the radius of this bend inside of the cable tray. Here it is at the end of the cable tray when it's dropping out. And here's over the side rail. Some precautions have to be taken. You have to make sure that the cable itself is protected from sharp edges. Most of the time you'll put a conduit on the side and let the conduit bring that cable out. So here's conduit dropout in the middle of the rung. Here's conduit on the side, and it'll be clamped to the side of the cable tray, and you can feed the cable into that conduit. Here's a highlight. Know the code. Cable trays are Article 392. And there's the dropout plate. Provides a curved surface for dropping cables to follow. Cable tray covers. A cable tray cover is primarily used to protect the insulation of the cable against potential damage caused by an object falling into the tray. Protect certain types of cable insulations from the damaging effects of direct sunlight. And here's another highlight. Cable supports in vertical trays. A cable hanger elbow is used to suspend cables in long vertical runs. Here's another highlight. Care should be taken to ensure that the weight of the suspended cable does not exceed the cable manufacturer's recommendation for maximum allowable tension on the cable. So we're going to use tie wraps and tie them to the rungs to alleviate that pressure. So that will support those cables. Cable edge protection. The solid bottom of a trough might be convex, concave, or flat. When two sections of tray are butted up together, the bottoms may be out of alignment. An alignment strip, also known as an H-bar, is placed between the tray bottoms to align the edges and protect the cable from scrapes. Here's a highlight. Vertical adjustment splice plates are used to change the elevation in a run of cable tray like an offset in conduit. So you can use these vertical adjustment splice plates and you can make an offset, a vertical offset. You need to elevate the tray. It's running along at 18 feet. You need to go up to 20 feet. You can put a 2-foot offset using these vertical adjustment splice plates. In general, 4 swivel plates are used to build an offset in a cable tray system. Once the proper angles have been calculated, proceed as follows. So here is your swivel plate, and you can bend this to make an offset to the desired height. Horizontal adjustment splice plates. Horizontal adjustment splice plates are sometimes used in place of horizontal elbows to change the direction in a run of cable. They're used when there is insufficient space for an unusual angle that prevents the use of a standard elbow. Expansion splice plates. Expansion plates are used at intervals along a run of cable to allow for thermal expansion or contraction of the tray to occur. Over long runs, significant changes in temperature can lengthen or shorten the tray, creating a great deal of stress in the support system. They may also be placed near expansion joints built into the supporting structure. For the expansion plate to function properly, the cable tray must be allowed to move freely on its supports. Any cable tray holding down devices used in an installation subject to expansion or contraction must allow for this movement. to use these expansion joints and allow this cable tray to expand and contract. Barrier strips. Barrier strips are used to separate certain types of cables from each other. This may be necessary for a variety of reasons. Separate or isolate electrical circuits, separate or isolate cables operating at significantly different voltages to prevent fire or ground fault damage from spreading to other cables or wires in the same tray, to promote neatness in the arrangement of the cables. So, 1.2.0 cable tray supports. You can use direct rod suspension, wall mounting, trapeze mounting, center hung supports, pipe rack mounting, center rail systems. Again, some places won't allow you to use the center rail system. Direct rod suspension. The direct rod suspension method for supporting cable tray uses threaded rods and hanger clamps. The threaded rod is connected to the overhead structure and to the hanger clamps that are attached to the cable tray. So they're using all thread and they're attaching it to these cable suspension or cable tray suspension hooks. You can mount it to the wall. You can put these, they look like shelf brackets, you adhere them to the wall, and then you can install the cable tray onto them. Here's a trapeze method. You're using all thread, but instead of attaching it to the hanger of the tray, you actually put a piece of unistrut across, and then the tray is supported to that unistrut. And this is center hung, and again, a lot of places won't allow you to do center hung. Wall mounting is accomplished using structural members attached to a wall. This method of support is often used in tunnels and other underground or sheltered installations where large numbers of conductors interconnect equipment separated by long distances. So in tunnels, wall mounting. Trapeze mounting shown in figure 15C, relies on a piece of channel or angle iron placed beneath the tray to support the weight. The threaded rod is then connected to each end of the channel. So here's an example right here where they used a piece of channel and nuts and washers, fender washers, square washer. They've suspended it from the structural members above it. Here's another one going the other way, supporting this X. Center hung support relies on only one rod at each position instead of two. The single rod is centered between the cable tray side rails. A sleeve, such as a short piece of small diameter PVC, may be placed over the rod to protect the conductors from the hanger rod threads. When the tray is center hung, care must be taken to balance the weight of the tray and its contents on either side of the hanger to prevent tipping. That's why they don't allow it. Pipe rack mounting. Pipe racks are structural frames used to support piping in industrial facilities. Some space is often reserved on the rack for conduit or cable tray. And then the center rail system. Center rail cable tray systems are lighter in weight than ladder, tray, and trough. They're easier to install and provide open sides for easy access when changing or adding cables. Of course, they generally have a lower weight capacity than other types of tray. For this reason, center rail trays is primarily used on light-duty applications such as sound, telephone, and data systems. In addition to its weight limitations, barrier strips can't be used, which limits the variation of power cable types that can be installed in the same tray. So here's a raised floor. The floor is above the concrete. They have these jack stands or these stands that hold the members of the floor. They're 2x2 tiles, and you can run your wire tray underneath and run all of the data cables in the computer room underneath the floor. It's a convenient system. A 15-degree change in cable tray elevation is most likely to require the use of vertical adjustment splice plates. Cables supporting communication and data systems are the types most likely to be found in supporting communication and data center rail cable. All right, let's see, where am I? All right, stop here and I'll start another video. 2.0.0 Cable tray loading. Explain how cable tray loads are determined. Determine the load applied to the cable tray supports. Identify the types of failure that can occur under load. Identify common installation requirements for cable tray. National Electrical Code requires that cable trays have sufficient strength to support all contained wiring, and they be supported at intervals indicated in the manufacturer's installation instructions. The load capacity of cable tray varies with each manufacturer and depends on the following factors: shape and thickness of the side rails, the shape and thickness of the bottom members, the tray volume, the tray material of construction, spacing of the rungs, the method used to support the tray, the method used to determine the allowable load, and safety factors applied. Here's a highlight. It says cables packed closely together can reduce the efficiency of the conductors. So avoid packing cables together. Try to space them out. Pack the cables loosely. If you need a larger cable tray or a second cable tray, you can mount it below it, or at the time of installation, if you think about it, you can put two cable trays, stack them one on top of the other. You don't want to overfill that cable tray. Determining the load on supports. Each support should be capable of safely supporting approximately 125% of the cable tray and the tray's full weight across the typical span. So you want it at 125% of the weight of the cable tray. And then length in feet of these supports, uniform load of the tray and cable, the full weight of the tray and cable divided by the total linear feet. Consider the case of a simple tray spanning only two supports. The tray bottom deflects downward from the weight of the cable, causing the side rails to lean inward. The amount of inward or outward movement of the side rails is a critical factor in the ability of the tray to carry the load. Failure under load. So failures include transverse, that's the rung or bottom, and longitudinal, the side rail. Transverse failures occur when the applied load causes the lower edge, the tension side of the rung, to stretch and permanently deform. At the same time, the upper edge compresses and is permanently crushed. So you have compression on the top and expansion or stretching on the bottom. And this cable tray ends up having a curve in it, and it's permanent. It won't come out. Longitudinal failures typically appear as bending or buckling of the side rails. The side rails of the tray have little resistance to inward or outward movement when placed under stress. If not positioned correctly, splices can create weak spots in a cable tray system. The load on the tray creates bending movements along the spans. Consequently, splices need to be located at points where there is limited stress. In practice, this means placing the splices near the hangers. The point of greatest stress is found at the center point of the tray between the two hangers. If the splice is located within 1/4 of the span's length from a hanger, it's protected from much of this stress. So they're saying, for example, if the span between hangers is 8 feet, splices should be located within 2 feet of the hangers. So I was hoping they'd give us a picture of the tray. All right. NEC Article 392 deals with cable tray systems along with related wire, cable, and raceway installations. Figures 21, 22, and 23 summarize the NEC requirements for cable tray installations. For in-depth coverage, always refer to the NEC. Cable tray manufacturers also provide detailed information instructions, and their products are designed to facilitate its installation according to the National Electrical Code. Figure 21, NEC regulations governing the use of cable tray. So this is ladder tray specifications for cable tray is in NEC section 392.10B1, and there's a maximum of 9-inch spacing between them. When these cables are between 1/0 and 4/0, you can't be larger than 9-inch. Wire size for single conductor cables and single insulated conductors, minimum of 1/0, 392.10B1A. Sunlight resistant, 392.10. Protection and cable tray use limitations, 392.12 and 300.22C2. So Air, steam, gas, water, and drain lines are prohibited in the same cable tray as electrical wiring. That's 300.8. Uh, NEC Article 392, Part 3, Construction Specifications for Cable Tray. The fittings are 392.100E. The side rails are 392.100D. Adequate supports, 392.100A. Smooth edges, 392.100B. Flame retardant materials, 392.100F. So all of these are in Article 392. All of the different regulations. You are allowed to pass through a wall or partition. You can pass vertically between floors. Passage through walls and partitions is 392.18D. You need to fire stop those openings if it's a firewall. You have to match the fire rating if it's a 1 hour rating or a 2 hour rating. You have to match it. You have intumescent pillows that you can put in here. If they get hot, if there's a fire and there's heat, those intumescent pillows will fill up and fill the voided area and not allow any air to move between the two rooms. Cable trays containing single conductor and or multi-conductor cables. Cables 1,000 volts or less on this side of the barrier. Cables over 1,000 volts on the opposite side. They have to be separated by a barrier. If you have cables that are over 1,000 volts to ground and cables of 1,000 volts or less to ground, they have to be separated by a barrier. Okay. They're allowed to run conduit to the bottom of this trapeze. It won't affect the cable tray. Make sure that the cable trays are well grounded. They have to be continuous, electrically continuous from end to end. You can't have any breaks in the middle. They have to be bonded together all the way. Here's a bonding strap across a splice plate. There's a vertical splice plate. So they're taking a bonding strap. Cable tray drawings. For a safe and functional installation, engineers design cable tray systems and specify their components. Due to the related hazards, these responsibilities must belong to highly trained professionals who spend a great deal of time considering every detail. They're going to figure out the strain and stress on the cable tray and the weight limits. Here's a sample cable tray system plan. So they've drawn this out. They've done all their mathematical calculations. This one with one line is turned down. If it has two lines, it's turned up. They're telling us a lot of things about this, where they're going, where these other places are going. But here's an X and here's a T, and they have turned up, turned down. Here's a flat 90 or an elbow. Here are all the different components they're showing in this drawing. Although experienced craft professionals will have little trouble reading the information on a drawing, new electricians may have some difficulty in visualizing the system in 3 dimensions. However, elevation drawings and other supplements help to provide a clearer picture of the system. Even new workers in the trade can then see how the system should be installed. Safety precautions for cable tray installations. Installing cable tray means working at heights above the floor. Consequently, workers must take the necessary precautions. In general, workers installing cable tray will use ladders, scaffolds, or lifts, work from the tray assembly itself, or a combination of all of these. You need fall protection. Keep the tray assembly area uncluttered during installation. Workers can easily trip over tools or tray fittings. Tools and parts can often fall off the tray and injure workers below. To help prevent these injuries, set up barriers beneath the tray assembly area. If you're working on the ground, never cross or move these barriers until the work above is completed. Learn to secure your lifeline properly and make sure your full body harness is a proper fit. So here they're using the buddy system. It's hard to reach behind you, so you have your buddy hook you up, and then you hook them up. Make sure that everything is latched and the person is safe. Here's basket tray. Basket trays offer many of the same advantages as ladder trays. It's lightweight and easy to install using special clips that attach to threaded rods. Basket tray is easily cut using bolt cutters or a basket tray cutter. One additional advantage is that it can be cut, bent, and connected to create T's, crosses, and elbows without the need of separate fittings. Section 2 review. The expected weight of an installed cable tray system is 400 pounds. Each support must be able to carry 500 pounds, 125%. When inspecting a long expanse of cable tray, you discover that the tray is buckling. This is a type of transverse failure. Cable tray must be bonded in accordance with, we'll have to look back. I believe it was 300.21. They were telling us that we have to bond it. It has to all be continuous electrically. We cannot have any breaks in it. Yeah, here, we'll just look back real quick. Where did we have that? We were looking at that. Let's see, there we go. There. 392.60B2 and 392.60B2. Where does it talk about the grounding strap? I guess it's 60. All right. 392.60. And we can also just look at our code book. We'll take a look and see what that says. 392.60. All right. Let's see here. 3.0.0, cable tray fill. Determine cable tray fill limitations. Determine the number of conductors allowed in a cable tray and identify derating factors for cable tray conductors. NEC section 392.20 covers the general installation requirements for all conductors used in cable tray systems, such as securing and running conductors in parallel. There are other related sections as well. For example, NEC section 392.56, cable splices are permitted in cable trays provided they are fabricated using methods approved by the National Electrical Code. Splices must be readily accessible and must not project above the side rail of the tray, while where they could be damaged. Here's a highlight. It says, where conduit or tubing is used, it must be secured to the tray with the proper fittings. So it can't be floating. And it has to be bonded. All the metal has to be bonded together. Number of conductors allowed in cable tray, 2,000 volts or less. Where single conductor cables comprising each phase, neutral, or grounded conductor of a circuit are connected in parallel, as permitted in 310.10G, the conductors must be installed in groups consisting of not more than one conductor per phase, neutral, or grounded conductor. This is to prevent a current imbalance in the parallel conductors as well as excessive movement due to fault currents, magnetic forces. So you want to group them. The number of multi-conductor cables rated at 2,000 volts or less that are permitted in a single cable tray must not exceed the requirements of 392.22a. The section applies to both copper and aluminum. So if all conductors are size 4/0 or larger, you can only install them in a single layer. Where all the cables installed in ladder or ventilated trough tray are 4/0 or larger, the sum of the diameters of the cable shall not exceed the cable tray width. Cables must also be installed in a single layer. So if they're 4/0 and larger, they must be installed in a single layer. For example, if a cable tray installation is contain 3 4/0 multi-conductor cables, each 1.5 inches in diameter, 2 250 kcmil conductor cables, each 1.85 inches in diameter, and 2 350 kcmil conductors, each 2.5 inches in diameter, the minimum width of the cable tray is determined as follows. So we've got 3 times 1.5 plus 2 times 1.85 plus 2 times 2.5. So they ended up with 13.2 inches. So we're going to have to go up to an 18-inch cable tray. That's the next size, above 12 inches. The closest standard cable tray that meets or exceeds 13.2 inches is 18 inches. Therefore, this is the required tray size. They all have to be installed in a single layer. Okay. All conductors smaller than 4/0. Per NEC section 392.22a1b, where all the cables are smaller than 4/0, the sum of the cross-sectional areas of all the cables must not exceed the maximum allowable cable fill area as specified in column 1 of NEC table 392.22a1. The table provides the appropriate cable tray width. To use this table, however, you must have the manufacturer's data indicating the cross-sectional areas of the cables. The steps involved in determining the size of the cable tray. 1. Calculate the total cross-sectional area of all cables used in the cable tray. Obtain the areas of each from the manufacturer's data. 2. Look in column 1 of NEC table 392.22a1. Find the smallest number that is the least, at least as large as the calculated number. 3. Look at the number to the left of the row selected in step 2. This is the minimum width cable tray that may be used. For example, determine the minimum cable tray width required for the following multiple conductor cables. 4, 1.5 inch diameter. 5, 1.75 inch diameter. 3, 2.15 diameter. So we're going to add all those together. They're actually going to find the cross-sectional areas by taking pi times the diameter squared divided by 4. So after they do that, we find that the area of one 1.5 inch cable is 1.7671. And we'll multiply that times 4, and we've got 7.0684. The area of one 1.75 inch cable, same thing, they're going to take the diameter squared times pi divided by 4, and it's 2.4053. To find the combined area of 5 of them, multiply that times 5, we've got 12.0265 inches. And then find the area of one 2.15 inch cable, add one of them, so we'll square it, multiply it times pi, divide by 4, and it's 3.6305. To find the combined area of the three 2.15 cables, multiply by 3, so we've got 10.8915. Now we'll add everything up together. Now we've got 29.98. We've got almost 30 square inches. Look in column 1 of NEC table 392.22a1. All right, let's do that. Let's take a look at table 1, or column 1 of the table. And let's take a look. So we'll go to our table of contents here, and we find that Article 392 cable trays is on page 265. So let's go to page 265. There. And I'm going to add 3 to it because that's just what happens. We're 3 pages behind. I'll click on page 265. And here's Article 392 cable trays. Now let's find that table. Or here's the table. Table 392.22a1, allowable cable fill area of multi-conductor cables. And we were just under 30. And that was ladder or ventilated trough or wire mesh, column 1. And we'll find 35. So we need a 30-inch tray in order to hold those cables. That ended up to be 29.98. I think it was what it was. Let's jump back real quick and we'll see if that's what it was. 29.98. Yeah, there you go. Look in column 1 of table NEC 392.22a1 and find the smallest number that's greater than 29.9864. And we found 35 square inches. So we look at the left, we find it's a 30-inch tray. So we can put all of those cables in a 30-inch tray. It's the minimum tray width that can be used for the given groups of conductors. Okay. Combination cables, where 4 or larger cables are installed in the same ladder or ventilated trough cable tray. The cables smaller than 4/0, the sum of the cross-sectional area of all cables smaller than 4/0 must not exceed the maximum allowable fill area from column 2. So we have to first add the 4/0 together and take that as a linear length and take that much of the cross-sectional area of the ladder cable tray away. So repeat the steps from the procedure used previously to determine the minimum tray width required for the multi-conductor cables having conductor sizes 4/0 and larger. Repeat the steps from the procedure used previously to determine the cross-sectional area of all multi-conductor cables having conductors smaller than 4/0. And multiply the result of step 1 by the constant 1.2 Add this product to the result of step 2. Call this sum A. Search column 2 for the smallest number that is at least as large as sum A. Look to the left in that row to determine the minimum tray size. So they gave us an example here. I'm not going to go over all the math, but basically they're taking these cables and they're finding the area of those cables, and the 8 cables times pi times the diameter divided by 4 was 23.162. Multiply the result in step 1 by 1.2. So 1.2 times the 14.98, and 14.98 is the 4-odd conductors. They added all of the 4-odd conductors together and got 14.98. So we'll multiply that times 1.2. We've got 23.1623. That plus the 23.1623. We ended up with 41.1383 square inches. Now we have to go to column 2. Find the closest number to 41.1383. It's 42 square inches. And then the tray width that corresponds to 42 square inches is 36. So let's go take a look at that. So here's column 2. And they said it was 42. So here's 42. And if we come over, we're going to see that we need a tray that's 36. I hope you can see that. That's awful small, isn't it? We found 42 square inches. And we come over to the left and we find that the tray size we need is a minimum 36-inch width, working with inside of the tray. Okay. Solid bottom tray where all the cables are 4-odd or larger. The sum of the diameters of all cables must not exceed 90% of the tray width. Where all of the cables are smaller than 4-odd, the sum of the cross-sectional area of all the cables must not exceed the maximum cable fill area in column 3. So we would use column 3 for smaller than 4-odd. We use 90% of the cross-sectional area for 4-odd and larger. Okay. Single conductor cables, conductors that are 1,000 kc mil and larger, are treated the same as multi-conductor cables with conductors of size 4-odd or larger. Conductors that are smaller than 1,000 kc mil are treated the same as multi-conductor cables having conductors smaller than size 4-odd. So in other words, if they're larger than 1,000 kc mil single conductors, they have to be in one row, one layer. You can't stack them. Ampacity of cable tray conductors. Section 392.80 gives the requirements for cables used in cable tray systems with rated voltages of 2,000 volts or less. Cables and cable trays use the same ampacity tables as other cable, which is with additional derating applied for the following conditions. The cable tray construction. Cable tray can be open or covered, solid or ventilated. Covered or unventilated tray is subject to ampacity adjustment. So if it's a solid bottom and it has a solid cover, you have to derate the ampacity. The cables available as either single conductor or multi-conductor cable. Cable with more than 3 conductors is subject to ampacity adjustment. For the purposes of derating, cable is separated into 2 groups, systems carrying 2,000 volts or less, and systems carrying over 2,000 volts. For AC section 392.80b, systems carrying 2,001 volts and above are subject to derating. So that's all derating factor, 392.80b. All right. Number of cables and cable configuration in the tray. Conductors installed in a single layer and those arranged in a triangular or square configuration must maintain the free airspace requirement of section 392.80 A2D and are subject to the ampacity adjustments listed in NEC 315.60 B and C. Okay. Well, all right. Inquiring minds want to know. Let's go look at 392.80 A2D. I would feel remiss if I did not do that. 392.80. 392.80. Let's see here and there. Where's 392.80? 392, that's .60. Single conductor. What am I not seeing in here? Combinations, capacities, single conductor. All right, I must have passed it up. Where is it? 392.60b. Oh, okay. All right, here's 392.80a 2D. Let's look. 392.80a2d. All right. So here's A1. Here's A2. And here's A2D. Where single conductors installed in a triangular or square configuration in uncovered cable trays with maintained free airspace of not less than 2.15 times one conductor diameter of the largest conductor contained within the configuration and an adjustment conductor configurations or cables, the ampacity of 1/0 and larger cables shall not exceed the ampacity of 2 or 3 single insulated conductors rated 0 through 2000 volts, supported on a messenger in accordance with 31015. Okay. All right. And what was the other thing we wanted to look at? Did it tell us the other thing? Yeah. Oh, 31560B and C. So let's go look at 31560B and C. Like I say, inquiring minds want to know. So 315, where would 315 be? That's close, that's 300. That's 305. 315. I should have just gone to the table of contents. I thought I'd find it. 315. There we go. There's Article 315.60, they said. Should have written it down. 60B and C. All right. 315.60B and C. There's 315.18. There's 315.32. 315.36. 315.60. There's table 315.60C2. Wait a minute, where's B and C? 315.60, ampacities of conductors, B and C. Engineering supervision. Under engineering supervision, conductor ampacity shall be permitted to be calculated using the following general equation. I don't know what that equation says, so I'm not going to worry about it. Let's look at C, tables. Ampacities for conductors rated 2001 volts to 35,000 volts shall be specified in table 315.60 C1 through C20. Ampacities for ambient temperatures other than those specified in the ampacity tables shall be corrected in accordance with 315.60 D4. Okay, very good. So C1 through C60. So see, ampacity of insulated single conductor cables triplexed in air. And that's what they were saying on a messenger cable. Oh, these are aluminum. If we're talking copper, here's what we would use here. So whatever size it was, 1/0. Temperature rating of conductors, 90 degrees Celsius, 105 degrees Celsius. That's 2001 to 5,000 volts. It tells us what the ampacity of those conductors could be. We'll have to keep our current rating to these tables. All right, let's move on. I know, it's complicated. You can do it for years and years, and then finally one day it'll make sense. A ladder style cable tray contains 8 4/0 cables, and each cable is 1.5 inch in diameter. A minimum width of the cable tray is 3 times 4, that's 12, so we're going to say 12 inches. 1.5 times 8, 12 inches. Which of the following is the least likely to result in ampacity rating of conductors and cable tray? D, open tray. Open tray, you wouldn't have to do any current ampacity derating. If it's covered, yes. If it's a tight cable configuration, yes. And the number of cables, yes. Okay. Okay, well, this concludes 26207 cable trays. I hope that I was concise enough. I was trying to get through it, but at the same time, I was trying not to leave out too much of the information. Uh, I'm sure you have questions. Ask your instructor. If you want, you can write your questions in the comments section, and I'll try to get back to you. I'll try to answer those questions. If you got something out of it, please give me a thumbs up. Consider subscribing to my channel, and like always, I'll see you on the next video. Thank you. Hey, this is Brian Young. If you liked my video, please give it a thumbs up and consider subscribing. I'll see you on the next video.